Chemistry 30. This is the second part of the EQ 3.3 video. So I left you with these examples to try. So we'll take a look at these, see what happens. So HPO4, H2PO4. So these are related. And let's see, this is related. So going from here to here, HPO4, H2PO4. So you can see it's accepting an H to go from here to here. So that means this is the base, or sorry, Bronston-Lowry base. And if I was to go in reverse, H2PO4 to go to the left to become HPO4, it's giving up an H, so that must be the conjugate acid. And of course, going from here to here, H2O to become OH, it's donating an H. So items that do that are Bronston-Lowry acids. And going backwards, OH to become H2O is accepting, so that is a conjugate base. So that's the scenario. That's what I have when that comes into play. So now I'll just compare the acids and the bases on that chart to see what happens in terms of what's stronger, what's weaker. So over here, the acids are H2O and H2PO4. So H2O is right here, and HPO4. HPO4 is only slightly stronger than H2O. Oh, I looked up the wrong thing here. I looked up this over here. I needed to look up the acid. So the acids are H2O and H2PO4. There's H2PO4 right there. So water, H2PO4, so you can see H2PO4 is stronger. Stronger acid, weaker acid. So H2PO4 was a stronger acid than H2O. So ideally what should happen here is that this is the strong base and this is the weak base. We should double check though. OH and HPO4. OH and HPO4. So as you can see, the one that lies further down is the stronger base, OH. So stronger base versus weaker base. So of course, by strong, we mean that this acid is going to give up its H more efficiently than this acid gives up, or sorry, than this acid gives up its H to HPO4. So if this transfer happens more frequently than this, then H2PO4 readily gives up its H to become HPO4. So most of my beaker that has this equilibrium will exist in the form of the reactant, and it'll lie mostly to the left. All right, looking at the last example, NH4, NH3 are closely related, so as we go from left to right, donate H+. So this is the acid, because it donates the H. And going backwards, NH3 to become NH4 accepts an H, so that would be the conjugate base. And going over here, we can see that OH to become H2O would be accepting an H+, and anything that accepts is the Bronston-Lowry base. If I was going backwards, H2O to become OH, it behaves as the conjugate acid. All right, so now looking up on the chart, comparing the acids, NH4 to H2O. NH4 to H2O, so we can see that NH4 is further up the list, so it is the stronger acid. So stronger acid, and this one here must be the weaker acid. And of course we know how the rest should turn out, but we should double check. NH3 and OH. NH3 and OH. OH is further down the list in the stronger base area. So as we can see, OH is stronger. So OH is the stronger base than NH3, which is the weaker base. So what this tells us that the strong acid and base, they readily have the H donation happening more frequently than the weak side. So NH4 will readily give up its H to form this So the equilibrium will lie to the right because of the stronger acid and base being on the left-hand side. Wanting to dissociate, wanting to do that H transfer. So you should be able to do the assignment. There's this questions 1, A, B, and C. There's an issue with B, though. I think something isn't on the chart. So if you make this little note, just make this little note and it'll help you out. H2O is the weak acid, and OH minus is the strong base. So if you have this little hint written down, you should be able to do it because it has NO2 and HNO2, and I don't think they are on that chart. So if you make that little note, you should be able to do that. All right, we'll see you again.